and I will introduce our first speaker. So our first speaker is Joshua Crotts. Joshua is a computer science senior at the University of North Carolina at Greensboro. He has been awarded several scholarships, including those from Samanage Success, Mary G. Murray, Stamps, and Charlotte and Dabney White. In addition, he has 2 published research papers concentrated in artificial intelligence research with Dr. Nancy L. Green. And Joshua's paper today is titled Binary Space Partitioning, a focus on rendering and compression algorithms. Welcome, Joshua.
Thank you very much. I'll go ahead and start sharing. All right, is that visible? All right. Good afternoon, everyone. Today I will be presenting my research on binary space partitioning with a focus on rendering and compression algorithms. All right, so let's get started. So we're going to begin with a brief overview to what computer graphics and data consist of, or in other words, why I decided to do this. Then we'll talk about rendering, what it is, and what an algorithm is, as well as how a computer draws things. And then we'll switch gears and there we go. Then we'll switch gears and talk about data compression with particular emphasis on something called quad trees. That'll be our little case study. After this, we'll actually jump into binary space partitioning and end off with a short discussion on some non-conventional ideas and research that I've thought of and experimented with. All right, so why did I do this? Well, with computers getting more and more powerful every year, we don't need to spend as much time designing complicated algorithms because the computer can process so much data so quickly. It almost seems pointless. In previous decades, several tricks were used to get the most out of the limited power of the hardware at the time, and those restrictions just simply aren't as prevalent anymore. And today we take for granted large storage devices, crazy high-end graphic cards, and CPUs, but that doesn't mean that we should be lazy with what we do have. So we're going to explore some of those older rendering and compression tricks. All right, so what is rendering? In general, it means to create something, but in computer graphics, it refers to the generation of an image using algorithms with software or hardware. So think about how this is used in video games, for instance. We have images, geometry, shapes, lighting, color, shadows, animation, and many more. All of these use rendering somehow. The important thing to note is that computers can draw simple geometry like rectangles, for instance, very quickly, though shadows and lighting are much, much more complicated. Okay, so we've been mentioning this term algorithm, but what is an algorithm? An algorithm is just a sequence of steps to complete a given task. You use algorithms every day without knowing it. Doing anything in your life generally has an algorithm consisting of very specific, precise steps to do it. Computers also use algorithms to do effectively everything, ranging from opening apps, reading and writing data, and you guessed it, rendering graphics. So there exists plenty of algorithms to draw shapes and graphics. So let's talk about a few. So the most basic rendering algorithm is called Painter's algorithm, which uses a back to front paradigm, exactly where the name comes from. The computer stores a list of objects to draw and draws the furthest one first from the viewer, and then renders objects on top of each other like it's drawing a scene, like a painter would. However, the issue is that it's severely limited, as you may be able to tell. It can fail on trivial shapes like polygons, which we'll discuss on the next slide. And it's also horribly inefficient. Shapes that are invisible to the viewer are unnecessarily drawn. Okay, so let's talk about a more important problem, overlapping cyclic polygons. Take a look at figure 2. Which polygon, according to Painter's algorithm, is going to be rendered first, A, B, or C? Well, it's ambiguous because they're all over top of each other. Of course, we can split up the polygons to induce some type of ordering, but that's also slow. Okay, there's also those algorithms that can draw those shapes, such as the classic scanline polygon fill algorithm, and I go into more detail about that and other similar algorithms in the paper. Okay, so let's jump to the ray algorithms, such as raycasting and ray marching. Some of you may have heard of an advanced trick called ray tracing, which is something that NVIDIA is very is advancing now, but that is a topic that's beyond the scope of this presentation. I just thought I would mention that. So what is raycasting? Raycasting is an older but cool and intuitive rendering algorithm. The idea is to cast a line called a ray from the camera or the viewer out into a scene that interacts with geometry. Then a shape is rendered based on its distance from the ray. We'll see this graphically on the next slide, but the advantage of this is that it's a very easy algorithm to implement, and it also allows for pseudo 3D effects used in an older game called Wolfenstein 3D by id Software. Though the drawbacks start when deciding how we determine what collisions or how collisions happen and how often to check for them. If we check every possible point along the ray, it's very slow. And conversely, if we check too infrequently, it can cause errors. Okay, so now let's talk about ray marching. Ray marching is very similar to ray casting, except that it marches the ray along to the nearest object in the scene and uses that as a baseline for where to begin the next step of the march. The advantage of this over ray casting is that there are less collision checks and it's still relatively easy to implement. Also, unlike ray casting, we never miss a polygon. So on the left here in figure 3, we see a raycasting demo that I've created, where the cursor designates our viewer, where the point of view starts, and a pseudo 3D scene is drawn. And on the right is a ray marching demo, where the yellow line is the single ray that's fired, and each circle is a step in the march. Okay. So now let's switch gears and talk about compression. What is it? Well, it generally refers to the reduction in size of something. So when we're talking about computers, it often means to make some file or data smaller in size. It's most commonly used when we're talking about photos or editing because raw photos are very large. Compression is very useful for big data and, you guessed it again, computer graphics, because storing raw data is inefficient and often just unnecessary. All right, so let's talk about quad trees, our case study. So quad trees are a type of image compression. The idea is this: as the name suggests, divide an image into 4 sections and then look for similarities among the colors, i.e. the pixels, in those sections. Then to actually do the compression, group those light pixels together, because storing a section of pixels is much more efficient than storing individual pixel data. So let's look at a rather cool example. We're going to compress the UNCG logo. All right, so we see that after compressing this raw image of the UNCG logo, which is around 4.2 megabytes, it's reduced by 31% in size. On one image, this may not seem like much, but imagine this on millions of images. And we can see how the grouping actually works. So the large squares indicate a large grouping of pixels of the exact same color. Okay, so there are other kinds of compression algorithms, hundreds of them for data, video, and more. All right, so now let's actually talk about binary space partitioning. So we've seen a form of it already in quad trees, but what else is there? Well, here's the idea. Instead of compressing the raw data, let's outright prevent the rendering of unnecessary graphics altogether. Remember Painter's algorithm? The issue with it is that it renders geometry that may be covered up by another shape. Binary space partitioning, in particular, uses a structure called a BSP tree, where BSP stands for binary space partitioning, this structure is covered in greater detail in the paper, but this solves the problem called the hidden surface removal or detection problem. So as suggested, this saves processing power, because why should we render something to the user when they can't even see it? All right, so now let's discuss the consequences of rendering and compression. So the issue is that there are several algorithms to choose from. Some are more difficult to implement than others, and many will have very limited use cases, such as the quad tree, for instance. We'll mention a potential fix for this in the next few slides, but also with quad trees, think about the structure of the image. If we shift or move it in any direction, the compression can drastically change. And images that have a lot of color or very disjoint colors may not save much space at all. All right. So finally, let's briefly mention some topics that I tinker with, called the occlusion rendering of polygons. Fancy name aside, this is very similar to the hidden surface removal problem and BSP rendering. So imagine a camera or the viewer as the yellow star in figure 6, with a bunch of triangles stacked on top of each other. If we render this scene from back to front, similar to Painter's algorithm, then we're going to draw a bunch of triangles that aren't visible to the camera, which again is very, very wasteful. It makes no sense to. So the idea is that we can use something called a scene graph, which is illustrated in figure 8, where these links, these lines in between the circles, indicate some sort of ordering or relationship between the objects. There are multiple ways to implement this, but for now, we're going to continue on to our last topic, which is another idea related to quad trees. All right, so let's mention this, triangular trees. So we render a scene, and instead of dividing it with squares, let's do it with triangles. The benefit with this is that this works with triangular scenes, obviously, but it can also be adapted to other scenes, such as hexagonal. The downsides, though, is that this isn't very widely used or tested. It has more limited cases than images, because most images are rectangular or square. And also there can be dead zones as indicated in this example by the red triangles. All right, so in conclusion, we discussed how compression and rendering algorithms work together with prime attention to how expensive it is on the CPU and the GPU. We've also explored various tried and tested algorithms that, while older, help shape modern computer graphics algorithms. Today, parallel rendering is frequently used, and again, that's discussed in detail in my paper. And finally, I'd like to add that most of these topics are best visualized. So I have provided links for my code at the end of this presentation. They're easy to download and nice to play around with because it helps illustrate these topics more. All right, so that's it. Thank you very much. I think you're muted.
I am